Guys, today we are talking about Hooke's law and friction, kinetic and static. Very nice, right? Fun time. Now, before we start that though, we're just going to do one little problem to just review Newton's law without friction or springs, okay? So we're going to start with a problem called Where's the Fire? Okay. Where is it? I don't know. Okay. So the fire alarm goes off. Whatever, okay. And a 97 kilogram firefighter slides down a pole with a constant acceleration of magnitude 4.2 meters per second squared. We want to know what's the upward force exerted by the pole on the firefighter. Okay, so we're going to need to do two things before we do anything else. We're going to need to draw a handy dandy free body diagram, and we're going to need to list out what our knowns are. Okay, so if we've got a firefighter sliding down a pole, what is our object that we're going to want to draw for the free body diagram? The pole or the firefighter? Yeah, the firefighter. Okay, so here's our little dot. The firefighter. Okay, so what do we have acting on the firefighter? Gravity, and then what else? One more thing. Yeah, we've got this like force that we're saying is being applied by the pole. We'll just call it F. Make our lives easy. Or you can call it FP for force of pole. It's up to you. Okay? And then our knowns. What do we know is the mass of the firefighter? You guys remember what I said? 97 kilograms. We don't use pounds in this room. We don't do it. Okay? What else should we be able to know? We should know what the force of gravity is, right? How do we find it? How do we find the force of gravity?
Multiply his weight by 9.8.
You multiply his mass times 9.8, not his weight. And since it's pointing down, should we multiply it by 9.8 or negative 9.8? You are. Okay, so what is the force of gravity on the firefighter? I would really appreciate an answer to my great question. I think you all seem like the kind of guys who could answer. Yeah, negative 950.6. What are the units? Yeah, there we go. It's taking you guys too long to answer that. Okay, and what did we say the overall acceleration is?
4.2.
Now, if you just had to take a stab in the dark, do you think that's positive or negative?
That's negative.
Negative. He's sliding down the pole. Okay. Now, what we're asked to find is the force of the pole. What does this equal? Who knows? But it'll be in newtons, okay? So, how do you think we should go about finding this?
Take the force of this current acceleration, subtracting it from the force of the entire acceleration.
Okay, so in regular terms, for step-by-step purposes, we're going to sum the forces.
Oh, yeah, sum the forces.
Sum the forces, okay. So, what are our forces that we're summing? There's only two. This shouldn't be a hard question.
Yeah, friction, normal force, thrust.
Why are you guys like this?
Air.
Friction, normal force, drag.
Critical velocity.
Okay.
Terminal velocity.
And what does this equal? It's not 0. It's
The sum of your
F equals what?
MA.
F equals MA. Okay. So far, so good, right? Okay. And remember that we're looking for this, right?
Yeah.
So how do we get that alone?
We plug in gravity. We plug in mass.
You don't have to, before you plug it in. We move stuff before we plug it in. What do?
We subtract gravity.
Yes, we're going to subtract gravity. So we're going to have that the force of the pole is equal to MA minus the force of gravity. Now what do you do? Now you can plug it in. Okay, so we're going to say that the force of the pole is equal to, what's our mass?
97.
Oh, you guys are so smart. It's not like I was pointing at the answer. Okay, what's our acceleration?
Negative 4.2.
It's a negative 4.2.
I'm gonna cry.
Why? And then minus our force of gravity, which is what? Okay, so when you plug all of this in, what do we get as the force of the pole?
543.2 meters.
Good job.
Or 12.
Did you say or 12? No, it's this. 543.2 newtons. Why were you guys standing up?
You're about to fight.
I mean, I think I'd sort of like to see that. Do you guys want to?
It'd be good entertainment these times.
It would be. We need some people fighting. Okay. Any questions about this one? No?
I think it's good.
Pretty simple, right?
Asa doesn't good.
Well, that sounds like a personal problem for Asa. Oh my goodness. Thrust is only present if it's like a rocket or something, you guys.
Spell red. LSTE.
Okay, let's talk about Hooke's law. So, new equation. Do any of you guys remember what it was? Who already took physics?
No.
Wow.
Friction equals force. Oh, friction equals.
This is Hooke's law.
Oh.
Hooke's law is with the springs.
Oh,
Okay. What the F stands for? What do you guys think the F stands for?
Friction.
Force.
Force.
Wow. Okay. Does anybody remember what the unit is for force?
Newtons.
Newtons. Good job. Okay. What do you think the K stands for?
Isn't that like a coefficient something?
Spring constant.
Okay, never mind.
Yeah, thank you for one person getting it right. Now, who remembers what the units are for the spring constant? Newtons per meters. Okay. Who remembers what the X is? Yeah, change in length. Whoever said change in time, why? Why did you say that? Okay, if it's a change in length, what do you think the units are? M for meters. So, does that make sense to everybody so far? So far, so good? Yeah? Yeah? Okay, well, now I'm going to draw a fun little picture, okay? One. Okay. So here, we're going to have a spring that's just chilling, okay? The spring is in what we call equal what?
Equilibrium.
Oh, okay. I can fit it in. I can't. It goes over it. Okay, whatever. Okay? So we'll consider this the equilibrium position of the spring. Okay? So if the spring's at this length, it's at equilibrium. Well, oh no, our spring is getting stretched. It has a change in length of x. Okay? And then it's like really stretched.
And then it just goes through.
And maybe we'll call this 2x, okay? So there's an equilibrium position. The distance that we have here, this change in length, is going to be how far from this equilibrium distance. Okay? Yeah, good. So our equilibrium is what we consider that our x is equal to 0 meters at. So if it's in equilibrium, it hasn't changed length at all. And right here where we've sort of doubled, you guys see that? Doubling the force is going to double the stretch distance. So doubling F doubles X. Now, with all of this fresh in our mind, we're going to do some examples together, okay? So let's see here. We have a spring with a constant of 21 newtons per meters, and it's stretched 3.4 centimeters. We want to know what force is required to cause this amount of stretch. So you're going to want to list your variables. What did we say K is equal to? You should have been writing it down. 21 newtons per meters. Yes, it is a spring constant. Okay? And then does anybody remember what I said the distance it was stretched is? Yes, so we said 3.4 centimeters. You guys, what is that in meters?
0.034.
Yes, good job. 0.034. What are the units? Meters. Okay, and we're looking for?
Inches.
We're looking for force. So we don't have to rearrange this equation at all. Woo! We're going to say that the force is equal to 21 newtons per meters times 0.034 meters. And what's that going to give us as the force required to stretch this spring? Yes, good job. 0.714 newtons. Wow, that was a really hard problem.
I don't know if I can take the next one.
We're going to get through it together, okay? So, the next one. Let's erase what we've got here. I'll leave the pictures up so you know you guys have something to reference because I know it's so confusing, okay?
I like pictures.
I'll leave them there. So, we're pulling on a spring with a force of 1.2 newtons. Okay? And it causes a stretch of 6.4 centimeters. We want to know what's the spring constant. So if F equals Kx, how do we rearrange to solve for K? You divide by X. So we are going to have 1.2 newtons divided by, what's our X in meters? Divided by 0.064 meters. And what's that going to give us as our spring constant?
15.75.
What are the units?
Meters.
Okay, we've got one more example, but I don't know if you guys can handle it. You think you can? No? Well, too bad. You have to do it anyways. Let's get rid of this. So we've already solved for F, and we've already solved for K. So what do you think we're going to be solving for next? So what is the stretch when you pull with a force of 2.3 newtons on a spring with a spring constant of 19 newtons per meter? How do we rearrange to solve for x? Yep, you're going to divide by k. So we're going to have 2.3 newtons divided by 19 newtons per meter. And what's that going to give us as our distance? Does it really teach you guys that?
0.12 meters.
Thank you. Ta-da! All right, so we're pretty good on Hooke's laws, right?
Yeah.
Yeah, okay, that's what I figured. So I'm just gonna erase all of this. Is Hooke's law hard? No, it's not. So if I give you a question about Hooke's laws on the test, will you be able to do it?
Yes.
Yeah, I think you'll be fine. Okay, so now we're gonna move on to friction. We're gonna start with kinetic friction, okay? So interesting fact about friction, it's fun.
Oh, I remember that. That's awesome.
Woo!
Is that an M?
It's an N. N.
No, what's the left of that? That's a U.
Yeah.
Oh, okay.
Okay.
That's U.
Wait, is it new or mu?
It's mu.
Wrong letter. I've been doing that before.
Okay, what do you think the little fancy F with the subscript K stands for?
Friction.
Force of kinetic friction. Force of K frick. This one. Anybody remember what the mu K stands for? Starts with a C.
The coefficient.
Coefficient of kinetic friction. Okay, and huh?
Is air resistance considered kinetic friction? No.
Friction is when two objects slide one on another.
Yeah, so you have to have it actually like touching a surface.
If you have normal force, then you can have friction. If you don't have normal force, no.
Oh yeah, so that answers what's the N stand for? Normal force. Okay, so let's talk about this. What do you think the units are for the force of kinetic friction? What do you think the units are for the coefficient of kinetic friction? They're not applicable because it has no units. No units.
It's simply a ratio.
Yep. And then what are the units for normal force? Newtons. Okay. You guys ready for an example? Oh, wait, I'm going to tell you one other thing. So, actually, no, I'll show you. You'll derive it. What were you going to say?
Are we going to go into like turbulence? Like Reynolds number?
I mean, I already in physics last year. You definitely took
Oh, God, that's cute. Okay, so this one's called, it's really good with, the fact that we just had Thanksgiving. Pass the salt, please. Will you pass the salt?
Are you doing a bartender slide or something?
No.
No, is it where you slide along the
Yeah, we are, yeah. You got to salt those mashed potatoes. And those what?
Tears.
The tears. Your tears already have salt in them. You'll be fine. Okay. So, someone at the other end of the table says, hey, pass me the salt. And feeling quite dashing, you slide a salt shaker with a mass of 50 grams. And maybe we should start making a knowns list. You have a mass of 50.0 grams in that direction. The shaker slides with an acceleration of magnitude A equals 0.6 787 meters per second squared. And comes to a rest at the desired location. What is the coefficient of kinetic friction between the shaker and the table? Okay. So we might have some more knowns, but we'll find out after we draw the free body diagram. Yeah, okay, so what's our object here? Our object is the salt shaker. This is like our objective is to find the coefficient of kinetic friction. Okay, what's acting on the salt shaker? The force of gravity, what else? It doesn't have thrust. It's not a rocket ship.
It's accelerated.
Normal force.
Normal force. And let's say, to make math easy, we're sliding it to the right. Yes, so we're going to have our friction
Is that like a weird force?
to the left. Okay. You guys bring me pain. True pain. Okay, so should this stay in grams? Okay, what is that in kilograms? Do you know how to convert to kilograms?
I forgot.
0.050.
Yeah, that's it.
Okay, so we're going to be using that as our mass. So let's look at our equation. That friction is, what's friction? Fun. Okay, what are we trying to find? So how are we going to rearrange to solve for the coefficient of kinetic friction? Okay, we're going to divide by that normal force. Okay, now, what is force equal to? This is a force of kinetic friction, so F equals, what's normal force equal to? It's going to be equal and opposite to what? Gravity. So it's going to be m times, what's the acceleration? G. Okay. Now, since it's normal force, we won't be doing it by negative g. It would be times positive g, right? This up. Yeah. Okay, exactly. Good notice there. We're just going to cancel those m's. So the coefficient of kinetic friction is going to be equal to our acceleration divided by g. What's our acceleration? You guys, what's our acceleration? 0.787 meters per second squared. And what's g? 9.8 meters per second squared. Okay, so what is our coefficient of kinetic friction? 0.0803, because I'm going all out. Okay, what are the units?
No units.
Good job. There are no units. This is our answer.
Do you have coefficient of friction with your system?
You just asked that earlier.
It has to be on a surface for friction to be present. Air resistance is considered like air friction, but it's not like friction. It's sort of like centrifugal force and how it's not real. Okay. Any questions so far? No? Okay, so let's think about, so suppose the coefficient of friction in this last problem wasn't 0.0803, okay? Instead, it's 0.120. Whoa, mind blown. Okay, so we're talking about this previous problem. We want to know the acceleration of the salt shaker in this case. So this is the coefficient of static friction. We know the mass is the 0.05 kilograms, but we're like, well, what the heck is the acceleration now? Like, I don't know. How are we going to find it? You guys, what did we get down to? We got down to that the coefficient of kinetic friction is equal to what over what? Acceleration over gravity. Okay, well, how do we solve for A? We're going to multiply both sides by gravity. So we're going to say 9.8 meters per second squared times the coefficient of kinetic friction, which here is 0.120. So what is our acceleration? What is it?
I pretty much got that.
What are the units? Yep. Good job. Okay, we've got one more example with kinetic friction. And you guys, this is really exciting because guess what it includes? Starts with a K. Kinematics. Woo! Okay. You guys should be so much more excited about everything that we're doing today. All right, so we got a baseball player, and he's sliding into third base with an initial speed of 4.0 meters per second. If the coefficient of kinetic friction between the player and the ground is 0.46, how far does she slide before coming to rest? Which means what's our final velocity? 0. Okay. And we want to find, basically, what's her delta x? So if you guys had to guess, where do you think we should start with this if we're trying to find delta x?
Find acceleration.
Yes, perfect. We're going to find the acceleration. Okay, you guys, how do we find the acceleration? What is the basically equation that we figured out? That mu k equals what? Acceleration over gravity. Okay. So how do we solve for acceleration? Yep, we're going to take gravity of 9.8 meters per second squared times that coefficient of kinetic friction, which is 0.46. So what does that give us as our acceleration? 4.50 what? 4.508. And what are the units? Squared, right? Meters per second squared. Okay, now that we have that, we need to solve for delta x. Who remembers the kinematic equations?
Oh, I remember them. I don't remember the kinematic equations. I know how to derive them. Take the integral acceleration.
Oh my, shut up.
Oh my God. Okay, so there are two equations that are going to have delta x in them, okay? We have delta x equals v naught t plus 1/2 at squared. And then the other one that has it in it is vf squared equals v naught squared plus 2a delta x. Which one do you think we should be using to solve for delta x?
bottom.
The bottom one. Why are we going to use the bottom one and not the top one?
We don't have.
Yeah, we don't have time. We ain't got time for that. Oh, God, why? Okay, so what's the first thing we like to do when we have an equation? What do we plug in? Starts with a Z. Ends with an eero. 0. So we know that VF is 0, so we're going to say 0 equals V naught squared plus 2A delta X. What do we do now? Starts with an R. We rearrange the equation to solve for delta X. So how do we rearrange the equation? What do we do with the V naught X, you guys? Or the V naught?
We subtract.
We subtract it. So we're going to have negative V naught squared equals 2A delta X. What do we do now? Yep, we're going to divide by 2A. Okay, so we're going to say negative 4 meters per second squared divided by 2 times our acceleration that we found of 4.508 meters per second squared. So with that, how far did she slide? 1.77 what? 5 meters. Still good?
Did I get the right answer?
Any questions? No? Okay, so we're gonna move on to static friction. Now, you might be thinking, well, how is static friction different than kinetic friction? Or you remember, how is static friction different than kinetic friction, you guys?
Static is stationary.
Yeah, static, stationary. So static friction is like if you're trying to slide something, but it's not moving. It's the friction that's keeping it from moving, okay? So it prevents motion from starting. It's like no motion. You're not starting. You're not doing this. Okay? So our equation here is F sub S max equals mu sub S in. So friction is still fun. Okay? Friction never stops being fun. So let's talk about what these stand for. Any guesses on what the F sub S max is? It's the maximum force of static friction. Okay? The maximum force of static friction. Then, what do you think the mu sub S stands for? Come on, you guys, you know this.
Coefficient of static.
Yes, the coefficient of static friction. And then finally, what does the N stand for? Yep, normal force. So once again, the units of the friction, the frictional force is going to be what? Newtons. Does the coefficient of static friction have any units? No, so we're going to be like, that's not applicable. You don't have units. And then what are the units of normal force? Newtons. Okay? You guys ready for an example? Y'all ready for this? Okay, so this example. It's called stranger than friction. Get it? Instead of stranger than fiction. You guys don't appreciate the effort I put into these. Just don't.
I
Okay.
didn't get that one.
Huh?
I didn't get that one.
So, students in a physics lab design an experiment to determine the coefficient of static friction between a 1.8 kilogram jack-o'-lantern. So we're going to say mass of jack-o'-lantern equals 1.8 kilograms. And the tabletop on which it rests. There's a basic procedure that's used to pour sand slowly into a pail, blah, blah, blah. I should probably draw the picture first. Okay, just so you guys can see what's going down. We have this little jack-o'-lantern, and it's attached to a pail that we are going to be filling with sand, okay? So the basic procedure is that you pour sand slowly into this pail. So slowly sand is going to be getting poured into the pail, okay? And the pail with the sand in it is then placed on a scale, and it is found to weigh 11 newtons. So the force of gravity on the pail is 11 newtons. Okay. So, we kept on filling it up until the pumpkin started to slide. So, what is the coefficient of static friction between the jack-o'-lantern and the table? Is basically what we're being asked to find. So this is how much the pail weighs when the jack-o'-lantern starts to slide. So until then, the jack-o'-lantern is doing what? Not moving. Okay, good job. Let's see here. Free body diagram of the pumpkin. This is our pumpkin. What's acting on our pumpkin?
Static friction.
Okay, in which direction? Left or the right?
Left.
Okay, what else?
The pail.
Force of gravity.
The force of gravity. Okay, what else?
Normal force.
Okay, and then one more thing. What's the one thing?
The pail.
Which would be considered the
Let's see.
I swear.
Wait, is it not?
No, it's tension. Thrust is only present if it's a rocket. Okay,
Why is there T?
because it's tension. So that's the jack-o'-lantern. What about the pail of sand? What would that one look like? What's the two things acting on it?
Gravity.
The force of gravity
Tension.
due to the pail and and tension. Oh my God. So, you guys, what is our equation for static friction? Yep, it's fun. Okay. What are we trying to solve for?
Static friction. Coefficient.
So what do we do?
It's F divided by S.
All right, so you might be thinking, what do we put in for this in this scenario, right? Because it would be the mass times the acceleration of whatever's going on. Do you think it's going to be for the pumpkin or for the pail?
Pumpkin.
Pail. Okay? So, because now the reason it's the pail is because that is what is making the jack-o'-lantern move. Okay? So whatever sort of it's like mass times acceleration is and everything, it's going to contribute to the acceleration of the pumpkin. Okay? So we're going to want to plug in 11 newtons for that. And then for the normal force that we're using, do you think we want the normal force on the pail or on the pumpkin? Pumpkin, because does the pail have a normal force? No. Okay, so how are we going to find the normal force on the pumpkin? times.
Weight.
So we're going to do 1.8 kilograms times 9.8 meters per second squared. So when we carry all of that out, what do we get as the coefficient of static friction between the jack-o'-lantern and the table?
0.62.
0.624. Are there any units?
No.
Nope. I do not believe there is static friction on your test. I think it's only kinetic friction. But if I put static friction on it, would you be able to do it?
Yeah.
Yeah.
Mm-hmm.
Donald, get off your phone.
Absolutely.
Okay, so we still got a little bit of time left. So let's say, suppose now that the coefficient of static friction is actually 0.55. So we're going to say it's equal to 0.55 now, okay?
What's the coefficient of 1? What's that
You could
represent?
have to be one.
It always has to be less than 1.
But what would 1 represent? If it was like 1.
It would basically be saying that the force of gravity is going in the opposite direction than before.
Yeah, like the static friction is so high that it's like moving it backwards, but static friction means it's not moving.
Okay.
Yeah. Okay. And so we want to know, is the weight of the pail and sand necessary to start the pumpkin moving in this case going to be greater than, less than, or equal to 11 newtons? If you had to guess, what would you guess? So now the coefficient of static friction is smaller than it was. So do you think the pail needs to weigh more or less?
Less.
Less, okay, it's going to be less than. But now here comes the real question. Well, what should it be? How do you think we should find it? So we changed this, right? And we're getting asked to find that. So do you think maybe we should use that equation? I think we should.
I think we should.
I think we should. How do we rearrange it to solve for that? Yeah, we're going to multiply by n. Okay. So we're going to say 0.55 times our normal force of the pumpkin, which isn't going to change. So we can use that. 1.8 kilograms times 9.8 meters per second squared is going to give us how much that pail needs to weigh. So please tell me, how much should that pail weigh? What are the units? Newtons. Congratulations, you made it through the notes. Give yourselves a pat on the back. But not too hard because you guys were acting up during class.